Hello, and welcome to Griffith Observatory's coverage of our summer solstice here in the Northern Hemisphere. Of course, it is the June solstice for those in the Southern Hemisphere where it's becoming winter. But indeed, we are here live from Griffith Observatory, and with me is Patrick So to help host the program. And we are very lucky to have with us today at noon our very own observatory director, Dr. Krupp. And he's going to be presenting Inhabiting the Meridian to tell you all about our Gottlieb transit corridor with our Meridian arc and what goes on there and why we are bringing this to you today at local solar noon. Um, of course, this program, as always, is brought to you by the City of Los Angeles, Griffith Observatory, which is owned and operated by the City of Los Angeles, the Department of Recreation and Parks, and these sorts of events are made possible in coordination with the Griffith Observatory Foundation, which is our nonprofit partner. And we're very happy to be here today to bring you this. It's an exciting time as we look towards reopening at some point in this summer, hopefully sooner than later. But today we are remote. Don't rush up here. Don't try and join us if you're nearby. Just enjoy the presentation here on YouTube. Now, you might be wondering what's going on. Why are they talking about local solar noon when it's after 12 noon? Well, what we're talking about is that moment in the sky where the sun is passing from the eastern half of the sky to the western. And it has that moment where it's highest in the sky. That depends on where you are in the time zone. So it's different for Los Angeles than it is for San Francisco, California. So it's different for every spot in the specific time zone, and you'll hear more about that. And we have an instrument here at Griffith Observatory that marks that moment in time and allows us to observe it. And that's what Dr. Krupp is going to tell you all about. Well, Patrick, what is a solstice in general, and why are we calling this the first day of summer?
Okay, well, it's the summer solstice here in the Northern Hemisphere, which means that the sun has traveled on its annual path across the sky, known as the ecliptic, and has attained its northernmost position on the ecliptic, which means from Los Angeles at local noon, the sun will be 79 degrees above due south, its highest for the entire year.
Yeah. On the first day of summer, the sun is at its highest point in the entire year. So it's going to do something quite special along our meridian arc as well. So we're very excited to bring that to you today. Now, some folks might wonder if today it's the highest in the sky. Well, it's also the longest amount of sunlight we'll get for the whole year. We'll start seeing shorter and shorter days, yet the weather will actually keep getting warmer and warmer because we're getting more energy. We're still receiving more energy than we're giving off at night. So we can't cool down enough to compensate for that extra energy we're getting during the day. So we're going to start seeing hotter and hotter days and less sunshine, though, which is interesting. So some of my favorite times in Los Angeles are here during the summer, of course. We're known as a beach culture. You have those beautiful palm trees. And the vista from Griffith Observatory is just glorious to be able to observe the sun. And one of the things we're also doing today is we're going to observe the sunset. We have sunset lines out on our sunset terrace where you can see we have predicted the direction the sun will go down today based upon the knowledge we've learned from science. So we're going to bring you that this evening as well. So tune in tonight for the sunset. And what time is that broadcast starting, Patrick? That one's starting 7:30 p.m. is when our stream will start tonight, right around there. So join us tonight for that as well. But right now, we have Observatory Director Dr. Krupp to talk to you about inhabiting the meridian here from Griffith Observatory. So thank you so much for joining us today, Dr. Krupp. It's a pleasure as always.
Thank you, Dr. Reitzel. Thank you, Patrick. And obviously, thank you, everyone, for tuning in today to Griffith Observatory Television. And observing with us the summer solstice, and in particular, a short time from now, as is just mentioned, local noon at Griffith Observatory's Gottlieb Transit Corridor on the first day of summer, at least in the Northern Hemisphere. I am Dr. Ed Krupp, Director of Griffith Observatory, and as a prelude to local noon, we'll spend a little time with the meridian, which is inextricably linked with local noon. Now, the meridian, of course, is a fundamental reference in the system of directions. It's just the line that runs on the ground from true north to true south. And wherever you go, there you are on some local meridian. Many monumental antiquities were intentionally aligned with it. And actually, our maps are usually oriented by the meridian. Example of a map of Washington, D.C., with north at the top and south at the bottom. The grid plans of many major cities are built to it. Here's Chicago in Illinois, just on the west side of the Lake Michigan, and all of its streets coincide with the meridian, the north-south streets. The design of Griffith Observatory likewise adheres to it. The vertical line going from the bottom to the top that you'd impose on the plan is in fact the north-south line of the meridian. Now, the meridian originates in the basic behavior of the sky and is a fundamental astronomical reference. It's probably the most familiar to people as the prime meridian, the meridian at Greenwich, England. The Greenwich meridian, which almost everybody knows, serves as the adopted 0 point for longitude on the Earth. And it's a primary attraction at the old Royal Observatory at Greenwich. People wind up, of course, visiting it. They wind up standing on it. They sit on it. And people, of course, observe on it. So the meridian is a north-south line. And you're just looking in the diagram to the north on such a line. And we identify those directions, north and south, through the most fundamental motion of the sky, its daily rotation. Thanks to the spin of the Earth on its axis, the entire sky seems to turn around a single unmoving spot in the sky. That spot at the image of stars, a time-lapse picture, is the celestial. And Polaris, the pole star, is fortuitously close to that position. The direction on the ground directly below the north celestial pole is, in fact, north. That is how the direction north originates. We wouldn't be talking about north in the first place if this were not so. We wouldn't be talking about north if the world did not turn. But as the world turns, of course, the sky delivers directions. And as the sky rotates around the the objects in the sky, the sun, the moon, the planets, the stars, all cross or transit the meridian. This is kind of a view of looking at the Earth as if it were inside a giant sphere that represents the sky. This isn't the way the universe is really put together, but from our position on the ground, we imagine there's like a giant bowl of sky over us. And in this view, from the outside, you can see the sun rising, going higher in the sky to the left, crossing the meridian at its highest point, and then continuing over to the west to set at the end of the day. The word meridian is rooted in words that mean midday or noon. When the sun transits the meridian, it is local noon. And when the sun is east of the meridian, it is ante-meridium, or AM, that is before midday. When the sun is west of the meridian, it is post-meridium, or PM, that is after midday. And for the record, no matter what you might read in the newspaper or elsewhere, noon is neither AM nor PM. The same is true for midnight. At noon and at midnight, the sun is on the meridian, and so it's neither AM nor PM. So the meridian then is a time and a place and a direction. And the meridian is also, as is visible here, the celestial arc that vaults the sky from the north point on the horizon through the zenith directly overhead to the south point on the horizon, on the opposite side of the sky. Every month, astronomy magazines like Sky and Telescope publish an all-sky map that bisects the chart from north to south, from up at the top down to the bottom, with the meridian line and the zenith, the point straight overhead right at the center, as is the case in this example. Now, from the surface of the Earth, the distinction between north and south is profound. This is why people, in fact, notice this kind of thing. They didn't simply abstract the idea of north and south, but they notice what the sky is actually doing. And the stars travel in circles around the north celestial pole. If you look to the south, however, the stars appear to follow longer, flatter trajectories. They're actually still traveling in circles because of the rotation of the Earth, but their migration looks strikingly different just because of the geometry of the situation and where you happen to be on the surface of the Earth. But the sky looks completely different in those two opposite directions, and people paid attention to that distinction. Our ancestors were aware then of these directional distinctions, and our ongoing use of them is really just a perpetuation of old habits. Evidence of these habits shows up in many ancient and prehistoric sites. For example, a natural rock shelter in Ventura County, California, is enriched with Chumash pictographs painted on the ceiling and elsewhere inside the shelter. But this location seems to have been chosen for this symbolic enhancement because by chance it opens due north, a direction that was certainly significant to the Chumash, as it is to most people. The slope of the ceiling permits a view of the northern sky and the north celestial pole. So when you are sitting in there and looking out the window of this shelter, you see the stars of the northern sky and the North Pole of the sky. A natural crack in the ceiling is on axis, and spirit creatures actually appear to be following that crack out of the shelter on an upward slant. The ceiling is slanted toward the North Pole sky, a destination of supernatural and shamanic power in Chumash tradition. Now, the same thing is true in principle, and it's deliberately expressed in monumental architecture in Chaco Canyon in northwest New Mexico. Pueblo Bonito, a large multi-story apartment complex, is oriented with the meridian, and on the plan with north at the top and the meridian indicated by the north-south arrow on the plan, you can see that there is a wall that splits the two halves of Pueblo Bonito, a D-shaped complex. And that, in fact, is then not only commemorating its orientation in north-south, but that wall bisects the two principal zones in the building's plaza, and the wall is still visible for visitors to see today. Beijing, in the People's Republic of China, is still the only world capital that adheres to a sacred cosmological plan. During the Ming Dynasty, it was laid out on a meridian, a north-south line, which the plan of the Imperial Palace of Beijing indicates here. That north-south line has been preserved even by the current regime. It's apparent in the ritual walkway of the Imperial Palace. This line was focused on the emperor, who held court in the Hall of Supreme Harmony, visible at the end of this view here, and the walkway that conforms to the meridian. The emperor was the sky's agent on Earth and the terrestrial counterpart to the North Celestial Pole. Just as all the stars circumambulated around the North Pole of the sky as the Earth turned, the visible face of the high god Shangdi, the court, circulated then around the emperor. Now in Egypt, the Great Pyramid at Giza and the rest of Egypt's pyramids are cardinally oriented. By incorporating cosmic order into monumental architecture, the Egyptians miniaturized the cosmos in a terrestrial setting and thereby transformed it into sacred space. And on this plan of the Giza pyramids, again, north at the top, south at the bottom, east and west on either side, and the monuments conforming nicely to those directions. The observatory of Guozhou Jing, a 13th century Chinese astronomer at Gaocheng in northern central China, operates like a sundial to establish and refine the calendar with shadows that are cast on a long, low meridian wall. The diagram shows how beams from the sun at two different angles, high and low, pass through a window up at the top of this tower and then continue to the left and fall upon that long, low wall, which can be seen, in fact, from above on the tower, looking down into the courtyard below. These principles were applied more elaborately in the 14th century by the Islamic astronomer and ruler Ulugh Beg at Samarkand in what is now Uzbekistan in Central Asia. He put an arc on his meridian. A sectional view of his instrument and building is visible there. And he did that to observe transits of the sun and other objects that he wanted to maintain a perspective on for timekeeping calendrics, and star mapping. Part of that monument remains today. That is the remaining piece of the entire arc that is still visible at Samarkand in Uzbekistan now. Europe developed its own calendrical revelations in architecture with giant meridian scales that were installed in churches. At first, they were intended to monitor the progress of the year calendrically, sort of as we're seeing Ulugh Beg did in his meridian arc, except they just let the thing lay out on the ground flat without the arc. And they intended to keep track of the calendar this way, and they were added to later by astronomers to make even more precise measurements of the sun's daily noon elevation. So at first, these were relatively simple timekeeping and calendar devices, but they evolved into rather elaborate research astronomical instruments, certainly by the 18th century. An aperture on a vertical wall rising beyond the south end of the calibrated meridian line permits a pinhole image of the sun to cross the meridian each day at local noon. And the point where the sunlight intercepts the line depends on the sun's noon elevation. This is a diagram drawn as part of the design for one of those Italian meridianas. The wall is on the left, the hole again is up at the top, and the line extends to the right. And at various angles, the sun shines a spot of light down onto the ground for measurement and visibility. As that aperture on the vertical wall lets that pinhole image fall, of course, it indicates a position, a very specific position linked to the angle of the sun on that day at noon. And because that angle depends on the date, the meridiana operates as a calendar. In this elevation, we see the meridiana that was designed by Ignazio Dante in San Petronio in Italy, in 14th century Gothic basilica in Bologna. That was in 1575. Dante's San Petronio Meridiana was actually never completed, and it was replaced in 1655 by a grander Meridiana designed by the astronomer Gian Domenico Cassini. And of course, that one may still be seen at the San Petronio in Bologna today. This 220-foot meridian is still embedded then in the cathedral's stone floor. And here, in fact, as the view in the opposite direction, and here's the sunlight crossing the meridian at local noon on the 18th of November, 2004. This can be found in other locations as well, of course. This is the Meridiana in the old upper part of Bergamo in northern Italy, and it's operating like clockwork, in this case, on the 14th of October, 2009. Formal observations of the sun's meridian transits persisted in national observatories. They were useful observations, and among them was the Paris Observatory, the cornerstone of which was laid on the summer solstice in 1667. So we're not only acknowledging today the summer solstice, but obviously the birthday of the Paris Observatory during the reign of Louis XIV. France adopted the axis of the Paris Observatory as its preferred primary meridian. Now, Jean-Dominique Cassini was invited to Paris to assist the development of the new Paris Observatory, and he became the first director. And extending the inquiry that he'd undertaken at San Petronio, which we saw a short moment ago, he constructed a large meridiana in the Great Hall on the second floor of the Paris Observatory, seen here. It's 96 feet, 10 inches long. He wanted the building to perform as an instrument, and he designed his meridiana to coincide with the meridian of France, which continues outside the building and just goes across the grounds. With it, he planned to obtain a more precise determination of the apparent annual motion of the sun. Now, despite the French predilection for a French prime meridian, the local Greenwich meridian, occupied by George Airy's transit circle, was officially adopted as the prime meridian of the world in October 1884 at the International Meridian Conference held in Washington, D.C. The drawing here, of course, shows that prime meridian transit instrument in its prime when it was first installed. Since that time, when Airy was England's astronomer royal, his transit circle was used in the service of British cartography. And the old Royal Observatory had been established in 1675 by King Charles II, who wanted it dedicated, quote, to finding out the longitude of places for perfecting navigation and astronomy. Well, long before England and France drew a line in the land for 0 degrees longitude, astronomy in medieval India also staked a prime meridian claim through Ujjain, about 400 miles south of New Delhi in India. The plan of that observatory, one of 5 that was built by Sawai Singh, is shown here. And the instruments, of course, are aligned north and south, and in fact, on a line that was considered by the ruler at the time as the prime meridian of India. So it was also believed at that time that this observatory occupied the Tropic of Cancer, the place where the sun shines directly down vertically at local noon, 23.5 degrees latitude. And so that also partly accounts for its status, geographically and astronomically combining this important principle into a spot on the landscape to build an observatory. Sawai Singh II, the Rajput ruler of Jaipur, built Ujjain in 1730, and 4 more great Samrat Yantras wind up making sculpture and architecture out of an instrument. We can see one of the other instruments at Ujjain here. And here at Jaipur, we have one of the most magnificent of these meridian devices. But there is also inside, on the side of this monumental building intended for measuring the passage of astronomical objects, there is a cardinally oriented room, entered by a door, and inside there is a pair of inscribed quadrants. And the room also permits light from the transiting sun at local noon to enter the darkened chamber through a pair of small holes that penetrate the southern wall. You can see one of those holes in this picture of the darkened room, and part of the light is glancing across the wall next to one of the quadrants on which the measurement is to be made. These projected pinhole images of the sun on the 2 quadrants then allowed Jai Singh and his associates to make direct observations of the sun's astronomical declination by this spot of sunlight, a little disk of sunlight, a pinhole image of the sun onto the inscribed quadrants that made then an accurate and a precise measurement of that angle, which in turn was linked to the calendar and to the progress of the year. Well, there are all kinds of meridians around the world. But anyone who collects meridian markers now must also navigate a course to Los Angeles. Griffith Observatory is cardinally oriented. It faces north, and its telescopes are aligned with the north-south axis. There, in fact, is the 12-inch Zeiss refractor in its dome with the axis and the telescope aligned on that meridian. In addition to that, the sundial out on the front lawn likewise is aligned with the meridian. That's in fact how it makes use of light and shadow to keep track of time. And in addition to that, the mirrors of the observatory's triple beam celestat or solar telescope are also on the meridian, because that is a convenient way to design astronomical instruments to follow the sky. Now, the Griffith Meridian is actually part of a singular and monumental public instrument, the Gottlieb Transit Corridor. There is really nothing else like this anywhere else in the world. This instrument is integrated into the observatory's new architecture on the west side, where the parallel glass walls that enclose it, they're 150 feet long and 20 feet high. They preserve below grade the observatory's signature vista of the western horizon. And this instrument demonstrates how the sky works through meridian transits of the sun, moon, and stars over the walled corridor. The corridor is about 10 feet wide, and it's bisected by the bronze meridian line set into the concrete floor. It extends the full length of the walls from one end to the other, which frame then the celestial meridian, and turn this astronomical abstraction, this artifact of geometry, into a visual experience. The architecture reveals the astronomy. So at the north end, the meridian line climbs a stairway constructed to ascend at the angle of the North Celestial Pole. We're at the top of that stairway here and looking to the south on that line, but then looking in the opposite direction up the stairway, we're also looking right at the same angle that one has to look in order to point something to the North Pole of the sky. The stairway and the banister were constructed to that angle. So at night, visitors can sight the North Star along the stairway's central banister. The fundamental character of Griffith Observatory is indicated right on the front of the building, where bronze letters declare Griffith Observatory. It is an observatory, and its job is to put people eyeball to the universe. Griffith Observatory is, of course, a public observatory, and the building is filled with instruments. All of them deliver real data and real experiences and transform visitors and visitors then into observers of nature and the sky through the instruments. So we are mobilized then at Griffith Observatory by the concept of the building as instrument. Now, the Gottlieb transit corridor is just another dimension of that immersive encounter with the sky. And there's more to it than the long glass corridor, the north stairway, and the bronze meridian line. At the south end, a tall and night black monolith supports the stainless steel foil up at the top. And on the ground, just north of the monolith, stands a massive and inscribed stainless steel meridian arc. Above it, on the inside face of the glass wall on the west, is mounted a large and heavy ecliptic chart. Now, the foil attached to the monolith is equipped with a complicated and technically advanced device, a hole. And as an object, say the sun, transits the corridor and shines, its light passes through the hole. Where that light falls depends on the angle the object makes with the horizon. An object reaches its highest elevation then when it transits. Well, the monolith and the foil permit light from the transiting sun to strike the meridian arc, where the sun's image, about 3 inches or so in diameter, announces the date on a scale inscribed with the months, the days, and the corresponding ecliptic constellation figures. So when this occurs, you can tell by the spot of sunlight, not only the month, not only the date, but also where in the background stars the sun is located. So you've got then the ability to do this, of course, not just for the time of summer solstice, but in fact, through the entire year, because the entire year is inscribed on that arc. Special emblems spotlight the solstices, the equinoxes, and the major standstills of the moon. People actually walk inside the transit corridor and watch all of this. They also watch it from the terrace above. Now, actually, Tycho Brahe already did something like this. In 1582, he fabricated and installed a large bronze engraved meridian arc for transit observations in Uraniborg, the castle observatory that he built on the island of Ven off of Denmark. We have, however, linked the meridian arc at Griffith Observatory, the meridian arc where the sun makes its daily noon transit, with that big star chart on the wall that I mentioned. And as the sun's light, and you can see that star chart just to the left, up high to the left of the meridian arc. As the sun's light reaches the center line of the meridian arc, it activates sensors that run the length of the arc. So in this view, the disk of sunlight is just encroaching on the meridian arc as the sun is close to local noon, but not quite on it. And of course, the actual meridian line, the very center of all of this activity, is the middle line on that metallic arc. Well, that central line there, the narrower line, is got a number of sensors that run its length, and they transmit a signal when the sunlight actually touches them. And they send that signal to the giant ecliptic chart. And at that moment, the signal prompts the illumination of lights up on the chart to mark the correct position of the sun among the stars of the background sky along the sun's yearly path, the ecliptic, as you can see the spots of illumination show here in the constellation Taurus. And they also light up, the signal also lights up the stars of the constellation that is showing on the ecliptic. So even though those stars are invisible in the daytime, on the ecliptic chart, they're made visible by the sun's own crossing of the meridian. So the meridian then is a place and a time and a direction. And when visitors arrive at this junction of Earth and sky, they occupy a place where space begins, a kind of a cosmic modem that downloads the sky. They connect what happens in the sky with place and time and direction here on Earth in a dramatic, precise, and content-rich revelation in light. The meridian is not then just an instrument or a concept. It is a stage, and the universe performs on it daily here at Griffith Observatory. Now, I am in my office at Griffith Observatory at the moment, but I am headed out now, out to the Gottlieb transit corridor, where I'll join you again as the sun approaches local noon. We'll follow the light of the image of the sun's disk and also get better oriented to the actual space out there. So in the moment, I now turn this back to Dr. David Reitzel and Patrick So of the observatory staff, and I'm making a break out the door. Thank you very much. See you in a short moment.
Well, thank you, Dr. Kropp. That was very interesting, and we can't wait to see you down in the Gottlieb Transit Corridor at our very own meridian arc down there. So that's going to be exciting to see our own spot of sunlight cross the arc, announcing the date, announcing the season. And, you know, we punctuate the seasons with these events here at Griffith Observatory. We now have been doing this since the winter solstice. We brought you the spring equinox, of course. And now we're doing the summer solstice again. And time is really just flying as we are, you know, observing these seasons. So being able to bring them to you live from Griffith Observatory here over the internet has been a real pleasure. And it's due to the help from the Griffith Observatory Foundation that we're able to do that. They make so much of our technology purchases possible that allow us to stream these events and bring you these beautiful images. So if you like what you're seeing, thank you so much for the folks that are making a donation on our fundraiser. Like I wrote in the chat, all the funds do indeed go to the foundation. They help make our school program be free of charge. And it's just fantastic, the folks that are helping. So now back to the idea of summer and why today is the first day of summer as we give Dr. Kropp a moment or two to get down there. Well, like we were saying, the sun is highest in the sky today. And that means the sunlight is the most concentrated for us. If you can imagine taking a flashlight, if you shine it straight down onto the ground or a table, it makes a very small spot of light. Well, all the energy coming from that bulb is hitting the table in that one little spot. So the sun, when it's high in the sky like this, its energy is also concentrated into a more narrow spot. You actually get more energy per little square area of the ground. And that's one of the reasons it warms up. You literally are getting more energy per little area. In the wintertime, the sun being low in the sky, it's like taking that flashlight and tipping it sideways so that the beam is going across and it spreads the light out. And then you're getting a lot less energy per little area. So in the wintertime, the sun is low in the sky, the light is spread out, you get a lot less energy. So it all makes sense why this happens. But why is the sun higher or lower? We might wonder about that. It has to do with the tilt of the Earth's axis. The Earth's axis is tilted by 23.5 degrees, which means that sometimes the northern pole is tilted towards the sun, if the sun's the sun, and as we orbit around, then it'll be tilted across, neither towards nor away. And then, of course, go to the next season, the southern hemisphere will be tilted towards the sun. So that tilt is more or less the same direction throughout the year. It's pointed towards the North Celestial Pole, as we call it. In fact, it defines the North Celestial Pole, and very close to that is the star Polaris, known as the North Star. So you can sight along our banister, like Dr. Krupp said, and you can see Polaris here from Griffith Observatory at night. At least when it's clear, you can. Of course, if there's clouds in the way, it makes it impossible. But that Polaris is not always our pole star. Our Earth, much like a spinning top that is a little off axis, wobbles. And it makes a wobble over a very, very long period of time. It's like 26,500 years, if I'm remembering right. So in the future, Polaris will not be our pole star any longer. I'm not remembering what the next bright star up there is, so I'm not going to take a guess at any of them, but we can certainly look that up and Google it for you. I'm wondering where Dr. Krupp is now. I don't want to babble on too much longer. I think we have a little bit of time here. The local noon isn't until 12:55, 12:56 or so to get to the nearest minute. So we have a little bit of time before he gets down there, and we'll get him oriented and make sure that everything is going well. By the way, we are lucky that it is a nice clear day here in Griffith Observatory today. We've been having some tropical moisture that's being brought up by a high pressure system that's off there, and there were some surprise thunderstorms a couple of days ago, which was very, very nice. So bright and sunny as it should be on this first day of summer here from Los Angeles. So we are going to be able to observe the local solar noon transit here from Griffith Observatory. I was a little worried about that yesterday. Sunset tonight should be glorious. Make sure you return to join us. If you've just tuned in, we are also bringing you the sunset tonight starting at 7:30 p.m. and the sun will actually go down about 8:08 p.m. along our sunset line. We have marked into our sunset terrace out there. Unfortunately, we're not open to the public yet. We are looking to do so sometime in the near future this summer. We'll let you know when we can do so. But for now, you're best off watching this program from home. You won't get a much better view from up here. So don't rush up here to take a look at any of these events. We can't handle the crowds when the building is closed. So I appreciate you tuning in here over the internet to watch these events. So now we're getting very close to the time that we should be close to getting to be able to go back to Dr. Krupp. So our switchers, feel free just to switch to his image whenever he is ready. And then I'll know that I can stop blabbering on. But I want to tell you about a couple other things we're doing here as we wait. Griffith Observatory, during the closure, we have developed a brand new online school program, and we were able to bring that to more than 10,000 kids while we were closed, which is a pretty good number considering we had to develop the program, test it, and all the rest. And it was indeed our foundation that made it possible for us to do that. So I'd just like to thank them one more time on that. And we're looking to continue to operate that program going forward. It lets us reach an audience that can't get here via bus. Our in-person school program has been running for years and years, and it's for 5th graders. And they actually get to come up here, see a planetarium show and all the rest. But our online program, we bring them a little, we call them elements, a little video element, all about our Gottlieb transit corridor and the Meridian arc, and we tell them what it does and how it works. So that's something we're not able to do with the regular students because the time it happens changes throughout the year. The time of local solar noon isn't always the same. Clock time and local solar noon time drift with respect to one another. And that's because the Earth's orbit is not circular. Earth sometimes travels faster in its orbit, and then it goes slower in its orbit when it's far from the sun. And that means that the sun's position in the sky isn't changing at the same rate throughout the entire year. So sometimes clock noon is ahead, sometimes it's behind. And then you add in the wrinkle, of course, of having daylight saving time. So it's a little crazy that we can track all of this stuff, but science, equations, it allows us to predict it all, and we can take care of it quite easily. So here from Griffith Observatory, we have all these things marked down on our calendars. You can check our website for information about sunset times and things like that as well. So now, Patrick, do you have any information about what's going on out there on the...
I do not. Oh, but if we can go to just a slide for the summer solstice. Oh.
And there I saw Dr. Krupp just very briefly there. So there's the slide of the summer solstice. Terrific.
Yep. So, basically summer solstice for us folks in the northern hemisphere, and winter begins exactly at the same time, 8:32, in the southern hemisphere. So they experience the winter, which is quite the opposite to what we're experiencing. But then 6 months from now, we'll experience winter solstice, where the sun is lowest in the sky at local noon, and we'll do another event at that time.
Yeah, in fact, it'll officially be summer just after sunset here in Los Angeles. So sunset is at 8:08 by the predicted time. We do have mountains off that direction, and we'll see whether we've adjusted for the mountains or whether that's the horizon time. So tune in for that excitement tonight to see whether 8:08 is the horizon time or the mountain time. We miss, at these times, we miss our astronomical observer, Tony Cook, that has been with us for so many years, because he would take into account all those things. Tony, if you've tuned in, hello out there from out there in the observer land. I know you're still doing lots of observing. Well, I think we're getting word that Dr. Krupp is about ready. So if that's the case, feel free to switch over to him and take it away from the Gottlieb transit corridor.
As promised, I am now in the Gottlieb Transit Corridor at Griffith Observatory, on the west side of the observatory, in fact, a little bit below grade of the primary building here, in the Gottlieb Transit Corridor, where we are about to observe local noon at Griffith Observatory. I've referred to the idea of it being the transit corridor, and transits over and over again. Transit can mean several different things in astronomy. But here, what it means is pretty straightforward. It is just the passage of an astronomical object, might be the sun, the moon, a star or planet, across the north-south line. And when that passage occurs, that object is as high above the horizon as it ever gets during the 24-hour cycle of the Earth spinning on its axis. And that means that the angle of that object can, of course, be measured and used to map any changes of position, if in fact it does change position. Now, the stars don't really do that, at least not very quickly, but the sun does. The sun moves in its path through the sky over the course of an entire year. That path is called the ecliptic. And it's not really the sun that's moving. We're the ones that are moving as we orbit the sun. But it appears, because of the way that the Earth is situated in its orbit and on its axis tilted 23.5 degrees to its orbit around the sun, that causes the apparent position of sunrise and sunset to migrate through the course of the year. We see the sun rising as far to the north as we ever see it on today, on the summer solstice, and it sets as far to the north as we shall ever see it. But we're here at local noon, where now the sun is about to transit the meridian. And we talked about the meridian a little earlier, and I just want to reemphasize again, it's actually more familiar to most people than we think. Everybody's heard of the Greenwich meridian, of course, the prime meridian, which is the meridian of longitude used to establish the 0 point of longitude. And that's just the longitude where the sun would be highest at local noon for Greenwich, England. Well, that's the Greenwich meridian, but here at Griffith Observatory, we've got the Griffith meridian, and it's right down there in the pavement of the transit corridor. Extends from the south side of this architectural instrument all the way to the north and reaches the stairway. That stairway ascends at an angle that is equivalent to the height of the North Pole of the sky. You can actually sight the North Pole and the pole star Polaris on that banister, because that is the position around which the whole sky is turning and making all of this seem to be taking place. So the meridian is on the entire corridor. It ends, of course, at the very top, pointing up to the sky. But inside the transit corridor, we have the meridian arc right by me now. Now, the meridian arc is intended to capture the light that an object might cast on the arc as it passes across the meridian. And it does that with, in fact, our giant 2001 night black monolith to the south of us. And as you ascend up the monument, you reach the stainless steel foil. And in the foil, there is that hard to describe, incredibly complex element I mentioned earlier, the hole. The sun shines through the hole, sends a spot of light down here to the transit corridor, and as the Earth turns, that spot of light moves closer and closer to the meridian arc. It's not on it yet. In fact, the spot of sunlight is just below me right now. It is edging up to the meridian arc because we're still a little bit ahead of local noon. But when that spot of sunlight reaches the meridian arc, it will encroach upon the arc, and where it hits the arc will indicate, as it crosses, the date. The meridian arc is inscribed with the months. May is shown here, and in fact, we've got April up above it, and so it keeps on going all the way up to the top to December. And then you have to come back down again on the other side. July is over here, really going the second half of the year up to December, and then the June part is coming from January down to June. The summer solstice point occurs when the sun is highest in the sky. That, of course, is today. From Los Angeles, it almost seems as though the sun climbs directly overhead. That's not really true, but you do have to turn your head very far up in the sky in order to see it at local noon. Likewise, the sun is very low in the sky at winter solstice. And these differences are extraordinarily clear. They're all related to seasons, and that's what made a difference to our ancestors. It was seasonal change that affected the availability of food and the need for shelter and clothing. And so people have been monitoring the sky as a signal of seasonal change really for as long as we're able to track back into history and even into ancient history. Well, the point of summer solstice then for the sunlight to drop on the meridian arc will be right here at the bottom, because the sunlight will be coming straight down from the hole. But in winter then, when the sun is very low, it'll be very high on the meridian arc. The meridian arc inscribed not only with the months, but also with smaller marks that indicate, in fact, the days of each month. And then near the months, there are small figures of constellations, ecliptic constellations, the constellations through which the sun travels over the course of the year. The spot of sunlight has now encroached on the meridian arc, and in fact it is crossing right on the line of summer solstice, and it will continue to move closer and closer to the central line, the actual meridian in front of me. Now, all of this so far looks a lot like some ancient or prehistoric astronomy, maybe with some Bronze Age additions, maybe a little Renaissance ornamentation, but this is the 21st century at Griffith Observatory, so wait, there's more. Because when this sunlight reaches the central line of the meridian arc, it activates these sensors, and these sensors send a signal to the ecliptic chart behind me. And the ecliptic chart maps out all of the constellations in the sky along the path of the sun through the course of the year. And if everything works, then you will see at the moment of local noon, this instrument here will cause the sun to light up its position on the chart along with the stars that are up there in the sky right now with the sun that we can't see. But they're up there, and the ecliptic chart will make it occur. So we're moving closer and closer to the central line. Just got a minute or so to go. And as you're watching this take place, it's well to think about the one sort of really serious problem. This is local noon, but in fact, if I'm looking at the time right now, it's about 12:52 p.m. Pacific Daylight Time here in Los Angeles at Griffith Observatory. So how can that be noon? Well, there are several things that make this not noon on the clock. the first and most important, probably from our perspective, we're on daylight time. We've just moved our clocks ahead an hour for the sake of the daylight time convenience. But much more important than that is the fact that the Earth's orbit around the sun is not a true circle. And so there are times when the sun seems to move more quickly and seems to move more slowly. That affects the time that our clocks give, because we're measuring clock time, which is uniform, with the sun, which is not. And then finally, we're not located right in the middle of our time zone, and so that affects it too. Well, we are just about having our spot of light crossing the meridian. And ladies and gentlemen, Griffith Observatory has to announce that unfortunately the ecliptic chart did not light today on the summer solstice. There is clearly there's clearly a systems error that's occurred, and so we obviously regret that fact. But if you come back tomorrow, you will in fact see it again, or anytime you come to Griffith Observatory for local noon, the effect takes place. But I apologize to report that we should actually have seen the chart light up at this moment, and it didn't. Nonetheless, we still have to prepare for the rest of the year. And think about this for a second. I said this is where the sun crosses at local noon in June, and in January it's way up at the top. And so if we're in January and then gradually we move through the months and the sunlight keeps changing its position until it gets down here, and then we're at nearly the end of June and it starts going back up again for the other half of the year, well, that all makes perfect sense. We've got to cover the whole year. But how does the meridian arc know that it's either this half of the year or this half of the year? How could it possibly do that? Well, the way it knows the answer has to do with the way the instrument is designed. We have to take a step over from our position right here, because at the solstices, we throw the solstice switch. And so I'm moving over now to where the transition takes place. On this particular panel, it indicates December, June, December, June. And at the time of the solstice, each one, in June and December, when we have the solstice occur, that's when we throw the switch for the other half of the year. Ladies and gentlemen, it's summer solstice, and you got another half year to go. Thank you.
Well, that was certainly interesting, and I'm not sure why our ecliptic chart didn't operate. I think it has something to do with our long closure. I'm sure somebody was doing some maintenance on something, and one of our computers, unfortunately, it is not behaving the way it should. So I'm sorry about that, folks. That's something that should have been checked, and perhaps it was, and it's failed in between. So we'll look into that and make sure that by tomorrow it's back up and running, and you can take a look at that ecliptic chart and see it operate. Tonight, we don't have any special sensors for our sunset. We have a line that is marked on our sunset terrace to show the direction that the sun is going to go down. We've predicted that, and we sure think we're going to get it right. But tune in to find out tonight at 7:30. So Patrick, how do you want to finish up today? What else did you want to talk to our crowd about? You were looking at the height of the sun in an image, and I don't know if you ever got to your point when Dr. Krupp showed up.
That was fine. I actually, there are some highlights for tonight as well, because after the sun has set, we're going to do stream some astronomical objects. And if I can have the slide on the screen, one of the objects that is prominent in our evening sky right after sunset is the planet Venus. I took this picture last month, but it's much higher in the sky. So we hope to get a scope on that and stream the planet Venus through a telescope so you can see its actual phase through a scope, which kind of looks similar to the moon, but it's without the features. And the moon is up as well, so it is very close to full, waxing gibbous. So we'll see if we can have the scope aimed at the moon and bring you an image of the moon through our telescope. The other object we might aim for tonight would be the planet Mars next to a star cluster called the Beehive cluster, which is in the constellation of Cancer the Crab. But we'll have to see if we can fit both the cluster and the star cluster and Mars in the same field of view. So those are kind of highlights after we observe the sunset on this solstice day.
Yeah, absolutely. It'll be a lot of fun to bring folks a view from our telescopes. So sorry about that. I paused there, got confused. One thing I want to talk about and mention is the generosity of folks. Some folks have indeed been making some contributions to our fundraiser on the YouTube stream. So I want to thank everybody for that. Griffith Observatory is owned and operated by the City of Los Angeles, the Department of Recreation and Parks. And, you know, we're here for everybody in the world. We're free to come visit us. And you can come in and take a look through our telescopes for free. You can wander our beautiful galleries and learn about space and science for free. But it does take our foundation, which is our nonprofit partner, to bring you a lot of these programs. And we greatly appreciate all of you that are helping us do so. So thank you to everybody that does that. And tonight, we will be back again to bring you a wonderful program where we'll celebrate the solstice and take a look. I do see someone in the chat was saying we're confused and we may have lost a signal. I'm not sure what happened there. Perhaps it was mentioning the computer, the signal not lighting up on our map. We're not sure why that didn't happen. A connection was lost on our chart, our star chart there. So anyway, well, tonight we will bring you the sunset. We will bring you some beautiful views from our observatory telescopes, and we hope you all tune in then.